Hello, welcome to the last section of this course, 16.9, the divergence theorem. Now, this divergence theorem, this section is quite a short one, but we will spend a lot more time in applying this theorem. The divergence theorem says, let E be a simple solid region. So imagine if you have a solid region and a simple one. So it's like maybe something like this. No, I don't like this. Let's say something looks like a ball. Simple solid region. Okay, and then S be the boundary of the surface. Okay, E is the solid, S is the boundary. So we can say this S is actually the boundary of E. Okay, now given the positive outward orientation, so the orientation is outward, going away from the solid. Think of that why we say the positive orientation of a solid should be the outward orientation, because if the solid is expanding, then the direction of that expansion will be outward. Okay, now and let F be the vector field whose component functions have continuous partial derivatives. This basically try to guarantee that when we do the divergence later on, the divergence will be continuous. Okay, the partial derivative will be continuous on an open region that contains E. Again, this is the standard way to say that this E here, okay, is contained in another open region larger than E, such that the derivatives applies even at the boundaries. Okay, even at the boundaries. Now, what this theorem says that if we want to compute the triple integral of the divergence of F, that's the same to doing double integral of the vector field itself, not the divergence, dot the directional surface. Now, the triple integral we have on the right hand side is also called the flux of that vector field F over E. Okay, so instead of saying that the triple integral of divergence of F over solid E, we may just say compute the flux of vector field F over solid E. Now, let's try to make sense a bit of this theorem. Again, the idea of how this theorem being explained is something I learned in my graduate study. My professor says the following: suppose you take any points inside that solid and you take the divergence. For each point, you take the divergence. So for this point, you have that divergence, and for the point next to it, it has divergence also. Oops. Now you will see that this part here actually being cancelled by this part. You will see basically because of the neighboring points and all the divergence together, okay, they will the divergence basically cancel each other for every interior points except at the boundary. Okay, so you see the one here cancel, the one here will cancel, the one here will cancel, everything cancel except for the ones in the boundary going there. Okay, which is basically the vector field dot the directional surface. And notice that this is actually represented by the normal vector ds, right? Okay, so think of that as like we do the dot product between the vector field and the normal vector to the surface of that E. So we actually do these two together, the F dot the normal vector. Okay, that's the idea of behind the what's that intuitive idea behind this theorem. Now, so what we will do today for this section, we will only apply this theorem. Okay, we start with question number, let's do number 2. Question number 2, and the question actually to verify if the divergence theorem is true. We will verify if divergence theorem is true. So what we will do is we will use the double integral on the left hand side, this one here, okay, and the triple integral on the right hand side, and show that if we compute them with these two different ways, we get the same result. Okay, let's start with double integral. So solution, double integral of vector field f dot d oriented s of surface the boundary of E. That's what we want to compute. Okay, now the vector field is x squared xy z, and E is the solid bounded by the paraboloid bounded by the paraboloid 4 minus x squared minus y squared. Now, notice that this solid here, not only the cap, not the paraboloid part, but also the bottom. Okay, so this the boundary of E actually consists of the paraboloid part union the xy plane part. Okay, now for the paraboloid part, let's z equals to 4 minus x squared minus y squared, right? So the gradient of z will be negative 2x I don't like this. I'm sorry. No. I want to call that g. Let g be g x y z be x squared plus y squared plus z equals to 4. So the gradient of g, which is normal to the surface, will be 2x, 2y, 1. And the orientation is upward, right? The orientation is upward for that paraboloid. Okay, so double integral over that surface of that paraboloid of f dot ds will be double integral. The f will be x squared xy, and the c will be 4 minus x squared minus y squared dot, okay, 2x 2y 1 dA, where the dA, the projection of that paraboloid to the ground, will give us this disk here. That's the disk D. Okay, this is the disk D. D is a circle centered at origin with radius 2. Okay, now then let me do the dot product, and I will get 3x cubed plus, I'm sorry, why 3x cubed? 2x cubed. 2x cubed, and then plus 2xy squared plus 4 minus x squared minus y squared dA. I wonder if anything cancels. Seems like nothing, huh? Okay, this is double integral over d of, let me pull the 2x out here so that I get x squared plus y squared, and then plus 4 minus x squared plus y squared dA. I hope you see where I'm going. I'm actually going to this direction. I will make it integral from 0 to 2 pi, integral from 0 to 2, okay, and then 2 times r cosine theta, right, 2 times r squared plus 4 minus r squared r dr d theta. Okay, and you will see this actually becomes 0. This term here later on becomes 0. Okay, and we will have 4 times area of D minus double integral from 0 to 2 pi, 0 to 2 of r cubed dr d theta. Okay, so this is 16 pi because area of D is 4 pi, right? Minus 2 pi times 1/4 2 to the 4th. Right, the 2 pi for this guy here will give me 2 pi. Okay, and then the other integral will give us that. Then this is 16 pi minus, what's that? For 8 pi, that's 8 pi. We are not done yet because this is only the surface for the paraboloid. Okay, now and then how about the plane, the surface of the xy plane? The surface is z equals to 0, but notice that for that surface the orientation, the direction is facing down, right? Okay, so the normal factor will be, the normal factor should be 0 0 -1. Okay, so double integral over the surface xy of that, it will be x squared xy, and then the z is 0 dot 0 0 -1 dA. The dot product is 0, so the integral is 0. Therefore, double integral over s f dot oriented surface s equals to 8 pi plus 0, which is 8 pi. That's if we just do the double integral. Now suppose we use triple integral, so we need to do the divergence. Triple integral over E of divergence of f dv. So that's what we did earlier, right? And we get that double integral equals to 8 pi. Now suppose we do the divergence. Okay, so our vector field f is x squared 2xy and then c. Is it right? Do I copy that correctly? No 2. Sorry, no 2. So the divergence of vector field F will be 2x, x, 1. Oh, I need to add them. It's a scalar. So that is 3x plus 1. Okay, now the triple integral over divergence of F over solid E will then be, I think I will make this into cylindrical integrations. Okay, from 0 to 2 pi, and then from 0 to 2, and then that's from 0 to 4 minus r squared of 3, what is x? X is r cosine theta plus 1 r dc dr d theta. Okay, and then if I integrate that with respect to z, we will get 3r cosine theta plus 1 times 4 minus r squared r dr d theta. Okay, as you can see, later on, this becomes 0. This part here becomes 0. Okay, it's just 1 times this guy, right? That's integral from 0 to 2 pi of integral 0 to 2 of 4 r minus r cubed. Actually, this is exactly the same integral we have earlier. Don't you think so? Right? That's the same integral we have earlier. Yeah, so we can confirm we get the same result at this point. Okay, so we can conclude. So double integral over the surface boundary of E of f dot oriented surface S equals to triple integrals over solid E of divergence of vector field F dv. That's for question number 2. Let's see question number 4. Question number 4, we have that vector field, and E is the solid cylinder with y squared plus c squared is less than equals to 9. So on the yc plane, that's a radius 3. So in 3 dimension, the solid looks like this. From from x equals to 2 to x equals to 0x. Actually, I think I draw it incorrectly. I'm sorry. This isn't correct. This is so wrong. This is so wrong. I happen to write it incorrectly. Yeah, it's supposed to look like this. It's parallel to x-axis. It's parallel to x-axis. My bad. It's parallel to x-axis. So it's supposed to look like this. It's parallel to x-axis. Okay, that's what it looks like. Let me do the triple integral first. I think that's easier. Solution So triple integral over solid E of divergence of f dv. If I want to compute that, divergence of vector field f will be 2x minus 1 plus 1, which is 2x. Okay, so the triple integral over 2x dv of that solid E is equal to, how should I do this? Let me make the parameterization as follow. The parameterization to be x r sine theta, r cosine theta. So I basically swap the position of x and z. Okay, so now I have, that is 2x, okay, and then r dx dr d theta, the theta from 0 to 2 pi, the r is from 0 to 3, and then x will be from 0 to 2. Okay, which if I integrate respect to x, I will get integral from 0 to 2 pi, integral from 0 to 3, x squared from 0 to 2, r dr d theta. That is 4, huh? Yeah, so that will be 4 times integral from 0 to 2 pi, integral from 0 to 3, r dr d theta. But this is basically the area of that circle with radius 3. So the answer is 36 pi. Okay, that's the triple integral part. Now the double integral part, I think, is painful. And we do the double integral over the boundary of E of f dot ds. Notice that the boundary of E consists of this part here. Let me draw it. Let me try to draw it. Okay. So the first part, which is, in my opinion, the difficult part to deal with, is this one here, the lateral area. The lateral area. Okay, that one is difficult. So that's the surface of the lateral area union. The front one, the one with us, this one here, such that the factor normal to it is this one. That's the surface of the front union the surface at the back, the one facing there. And the thing is, we need to parameterize one by one, right? Okay, let's do this front one first. Okay, the surface at the front, that's x equals to 2. Okay, and the factor normal to it will be, because it's facing forward, that will be 1, 0, 0. Okay, the factor field on that front surface will be, what's that? The x is 2. The x is 2. Where's that? So 4, negative y, and z. Right? So when we do the double integral over front surface, that will be 4 negative y z dot 1 0 0 dA. Okay, but the dot product is actually 4 times, double integral over 4 times of that thing. It's actually the same to this as at the back already though. that is equals to 4 times 9 pi, which is 36 pi. Okay, now how about the one at the back? The one at the back, that's when x equals to 0, so the normal factor will be, and it is facing backward, right? So -1, 0, 0. Now, but the factor of field on the surface at the back will be, the x is 0, -y, and z, which when we do the dot product, that will be 0. So double integral over SB of f dot ds, that will be double integral over 0 dA. I'm sorry, that's a SB 0 dA, that's equals to 0. Now the lateral part is hard. The lateral part is hard. Why? Because you see, this is the x, this is the y, this is the c, right? Okay. I need to parameterize that in a way such that the normal factor is facing out. I wonder if you remember how we parameterize that. Okay, that's r vector field r x theta. Okay. That r is x r sine theta r cosine theta. I think from the way it is being done, I think we better use cosine here and sine here. Just to make sure that the normal will be facing out later on. So r prime x, no, I should not say it that way. R sub u will be, r sub x will be 1, 0, 0, and r sub theta will be 0, negative r sine theta r cosine theta, whose cross product is 0, r cosine theta, negative r cosine theta, negative r sine theta. Oh, I don't like this. The reason I don't like this because this is actually facing in. This is facing in. No. You know what? Reverse the order then. So we do this one. R theta cross R x. Just to play around. Okay. Now then, what else do I need? So double integral over lateral surface of f dot ds will be double integral. What is the f again? X squared negative yz. So x squared negative y z dot 0 r cosine theta r sine theta dA. Let's do it this way. This will be dx dr. No, dr. I'm sorry. I'm so wrong here. It's not r though. It's theta, no r. No, it's the r. The radius is 3. What am I doing? And the radius is 3, duh. So this should be 3 here, should be 3 here, this should be 3 here, this should be 3 here. And yeah, once I write the variable of integration, then I start realizing that. Okay, but when we do the dot product, the x will be from 0 to 2, and the theta from 0 to 2 pi. 0 to 2 pi, and x is 0 to 2. But the dot product for x is 0. Then minus 9 cosine square theta plus 9 sine square theta dx d theta. This is 9 integral from 0 to 2 pi of cosine 2 theta times 2 d theta, which will be 0. Okay, so then double integral over the boundary of that solid E of f dot ds oriented s will be 36 pi. That's for the double integral over the front surface at the front, plus 0, which is the double integral over surface at the back, plus 0, which is double integral over the lateral area, lateral surface, which is 36 pi. Okay, so we do confirm that again, that if you use divergence of the triple integral, that gives you the double integral over the whole closure of the solid, the surface that encloses that solid. Number 6. Suppose we have that vector field, and S is the box enclosed by planes x equals 0, x equals a, y equals 0, y equals b, and z equals 0, z equals to c. Let's try to sketch that first. So let's say we have this, and then the box actually from x equals to 0 to x equals to a, y equals to 0 to y equals to b, let's say this is the b, and z equals to 0 to c equals to c. And the question is, compute double integral over the surface of this solid, of this S of f dot ds. According to divergence theorem, this is triple integral over solid E of divergence of f dv. Okay, so what is divergence of f? Divergence of f will be 2xyz plus 2xyz plus 2xyz. Oh, that is 6xyz. And the triple integral therefore becomes integral from 0 to a, 0 to b, 0 to z, 0 to c of 6xyz dz dy dx. I think this is a lot easier to compute, huh? Don't you think so? Because the domain is quote-unquote rectangle, right? And the integrand is separable, right? So I can say this is actually 6 times integrals from 0 to a of x dx, integral from 0 to b of y dy, integral from 0 to c of c dz, z dz. Okay, so this is 6 times a squared over 2 b squared over 2 c squared over 2. That's 3 over 4 a squared b squared c squared. Okay, now can you imagine if we try to do it using the surface integral instead? Let me give you some idea what will happen if you actually do that. Okay, notice that this surface S consists of 6 surfaces. This S consists of the surface at the front, union the surface at the back, union surface at the top, union surface at the bottom, union surface on the left hand side, union surface on the right hand side. Okay, the front one will have the factor, normal factor 1, 0, 0. Okay, the front one, this one here, the factor normal to it will be 1, 0, 0. Okay, the back one will have normal factor negative 1, 0, 0. Okay, the one on the right will have normal factor 0, 1, 0. The one on the left will have normal factor 0, negative 1, 0. The one on the top will have normal factor 0, 0, 1. The one at the bottom will have normal factor 0, 0, negative 1. So suppose I want to compute one of them. Okay, let's say I do the top one. Okay, double integral over surface on the top of f. Now the f at the top is when z equals to c, right? So cx squared y, cxy squared, c squared xy dot. At the top, that will be 0, 0, 1 dA. Okay, so this is basically double integral over that rectangle from 0 to a and then 0 to b of c squared xy dA. Okay, which will give us c squared over 4 a squared b squared. Okay, now you will see if you put the one at the bottom. So double integral over s at the bottom. Okay, notice that at that time the z equals to 0. Okay, that will be 0, 0, 0 dot 0, 0, negative 1 dA. But that's just a clearly 0 case, right? Okay, the computation is still easy in my opinion. It's just like you need to break it into 6 double integrals to compute that, which is it's just tedious. You know, it's like you know what will happen, you know how to do it. It's just you need to do it repeatedly, 6 same things. Okay, yeah, but if you do it using divergence theorem, you see it's a lot more convenient, right? Okay, the amount of work I have on the left hand side and right hand side, as you can see, the left hand side I already finished the computation. On the right hand side I only done with the 2 surface integrals, while I'm supposed to do 6. Okay, let's go on. How about number 8? It gets more and more interesting though once we get more complicated shape. So we have that vector field, and S is the sphere with center at the origin with radius 2. So let's do the divergence first. Divergence of vector field F will be 3x squared plus 3y squared plus 3z squared. That's 3 times x squared plus y squared plus c squared, where the S is the sphere. Okay, so what happened is the solid, maybe I should say let S be the boundary of solid E. So the double integral over surface F of f dot d oriented S by divergence theorem, there will be triple integral over solid E of divergence of f dv. Okay, so that's triple integral over solid E of 3 x squared plus y squared plus c squared dv. But if we think about this, this is a sphere, a ball centered at origin with radius 2. So that will be integral from 0 to 2 pi for the d theta, integral from 0 to pi for the dv, 0 to 2 for the d rho, okay, and then 3 rho squared, that's for this guy here, that's the 3 rho squared sine phi. Okay, now but this is equals to 2 pi, maybe I slow down a little bit. This is integral from 0 to 2 pi of d theta times integral from 0 to pi of sine phi dv times integral from 0 to 2 of 3 rho to the 4th d rho. The first integral is 2 pi, the second integral is 2, the third integral is 3/5 times rho to the 5th. Okay, 32, 64, 128 times 3. 128 times 3, 384. That's 384 pi over 5. Okay, and that's it. That's for number 8. Okay, next one, number 12. Let's see, number 12. That's the vector field. S is the surface of the solid by the cylinder and planes and xy plane. Oh, okay, so we have this cylinder on the ground, and then that plane. So seems like that plane will look like this. Like slanted. Okay, and then we have the bottom also. So S be the boundary of solid E. The divergence of F is 4x cubed 0 4xy squared. Why I make it factor, huh? So this is 4x times x squared plus y squared. Okay. Now then, therefore double integral over surface S of f dot oriented surface S equals to, by divergence theorem, triple integral over solid E of 4x x squared plus y squared dv. Okay, I will make it into cylindrical integration, integral from 0 to 2 pi, integral from 0 to 1, right? And then as for the height, this will be integral from 0 to x plus 2, which is r cosine theta plus 2, right? Now then, the integrand, we have 4 times the x will be r cosine theta times x squared plus y squared is r squared, okay, dc, and then r dr d theta. Okay, that's integral from 0 to 2 pi, integral from 0 to 1 of 4r to the 4th cosine theta, r cosine theta plus 2 dr d theta. If I split this, I will get 4r to the 5th cosine squared theta dr d theta plus integral from 0 to 2 pi, integral from 0 to 1 of 8r to the 4th cosine theta dr d theta. And you can see, because it's an integral from 0 to 2 pi of cosine theta only, that will go to 0. Okay, so we only worry about the guy on the left hand side, the first term. Okay, that will be 4 times integral from 0 to 2 pi of cosine squared, that's 1 plus cosine 2 theta over 2 d theta, times integral from 0 to 1 of r to the 5th dr. And I know again this will integrate to 0, so I get 4 times pi times 1/6, so I get 2 pi over 3. Okay, let's see what happened with number 18. I actually like number 18 for some very nice reason. In number 18, we have this question here. Okay, let F be this is the vector field. Find the flux of F across part of the paraboloid that lies above c equals to 1 and is oriented upward. So this paraboloid here, this surface here is given by c equals to 2 minus x squared minus y squared. Now notice that the flux over that paraboloid, just the paraboloid, that is not a closed surface. It's not a solid. It's not a solid. Okay, that's not the surface of the solid. The surface of the solid is this S union, let's call this B here. Okay, so the boundary of the solid that we want to talk about is equals to surface S union surface B. Okay, now what we want is just double integral over S f dot ds. That's all we want. Okay, now if you try to compute this, trust me, it will be very painful. It will be very painful. Okay, I will not do that though. I will not do that. I will not do that. But what I want to say is the following. Okay, notice that double integral over this surface S plus double integral over surface B f dot ds is double integral over the boundary of E, at which we can use divergence theorem. That's triple integral over E of divergence of f dv. Okay, so if we want to compute double integral over S surface S only, the paraboloid part of vector field f dot oriented S, that is the same to triple integral over solid E of divergence of f dv minus double integral over the bottom f dot oriented surface S. Okay, and that's what we will do. That's what we will do. Okay, let's start with the first integral. Okay, divergence of vector field f. You see, the nice thing about divergence is you do the derivative, right? And you see, when you do the derivative of the first component respect to x, that's 0. The second component respect to y, that's also 0. The third component respect to z, that's 1. Okay, so triple integral over solid E of 1 dv, that's basically the volume of solid E, is it right? Which is given by 0 to 2 pi, 0 to what? 0 to, hold on, that's up to c equals to 1. C equals to 1 means, yeah, 0 to 1, the radius is 0 to 1, and the integral, the z will be from 1 to 2 minus r squared, right? R dz dr d theta. That is integral from 0 to 2 pi, integral from 0 to 1 of r times 2 minus r squared dr d theta. That is 2 pi times r squared minus r to the fourth over 4 from 0 to 1. That's basically 1 minus 1/4, that's 3/4. So that's 3 pi over 2. But we are not done yet. Okay. Now let's deal with the bottom, surface at the bottom. The surface at the bottom has normal factor. Remember, because it's facing down, then the normal factor will be 0, 0, -1. And the z is equals to 1. Okay, now what happened then to the vector field? The vector field at the bottom, which means the c equals to 1, will be, when the c equals to 1, it will be tangent inverse y squared, comma, natural log of x squared plus 1, comma 1. Right? Now, you may be afraid with that tangent inverse y squared, natural log of x squared plus 1, but the thing is, when you do the dot product, you only get that -1. Right? So double integral over the bottom of f dot oriented surface S will be double integral over that domain D, which is the disk with radius 1, okay, of -1 dA. That's negative pi. Okay, so what happened to that double integral over the surface that we want to compute? That will be 3 pi over 2 minus negative pi. Okay, which is 5 pi over 2. Okay, I hope it makes sense right now. That's for number 18. So what happened here in number 18 is basically telling us this lesson. Suppose later on I need to compute the surface integral over a vector field. Let's say this is surface S of f dot d oriented S. One of the technique you can do is actually you look for the enclosure of that surface to form a solid. So I enclose the bottom. I call that B, where S union B now the boundary of solid E. Okay, now then double integral over that S plus double integral over that B of f dot ds is equal to triple integral of the divergence of vector field F dv over the solid E, right? Okay, so instead of computing this, which is maybe messy, okay, especially if the vector field is fugly, okay, what we can do is you compute the divergence and this part and you subtract them, okay, and then we subtract them. That's the idea that we can do if you look back to surface integral in 11.7, I think. Either in 11.7 or 11.6, I don't remember precisely. I think it's 11.7. We can use this technique actually. Okay, let me stop here and then give you the suggested homework. 16.9. I would like you to work on number basically number 1 to number 18. I think that should be good enough. 1 to 18 except 15 and 16. 1 to 18, skip 15 and 16. That's because you need the graphing calculator thingy. Okay, that's for today. See you then.